I'm going to follow on the last talk and look at what controls the amount of liquid and ice grown from oceans. The punchline is, in this case, salt. So I'm going to look at the role of impurities in ice as you solidify it. And one of the largest sort of most accessible natural laboratories for growing ice in salty oceans is, of course, in the polar regions, where you solidify maybe 6 million square kilometers of ice in the Arctic and about 13 million square kilometers of ice in the Antarctic every year. Another large geophysical laboratory for solidification where there's impurity in the Earth is solidification of the inner core. And this occurs when, due to secular cooling, the sort of stew of liquid iron and soluble impurities like sulfur cool and solidify at the center of the Earth. That solidification rejects the impurities, and you're left with basically a pure solid iron inner core. Those impurities in turn drive compositional convection within the outer core, and that's the outer core. That's the convection that gives rise to the Earth's magnetic field. So the solidification of eutectics, or binary alloys, gives rise to some interesting patterns both in solidification and can drive some of the convection that results. So first I'm going to look at ice formation in salty oceans, and I'll review solidification of binary alloys and that sort of thing. And then I'm going to look at the effects of oceanic flows as well. And I'm going to do that sort of generally, both within the Earth's oceans and then also looking at settings on the inner core. So to just set the stage, first off, this is a picture of the fraction of the Arctic Ocean which is covered by ice versus the mean thickness or draft of that ice. And you see that it's got a strong peak around about 2.5 meters thickness. Everything on the upper end of this scale is essentially ice in the Arctic Ocean, which is formed due to processes like ridging, rafting, flows interacting together with one another sort of mechanically. And so if you ask a question about how does the ice behave for thicker ice, you need to know the physical properties of that ice, and the physical properties are really set by what happens at the smaller end of this distribution. So for ice that's at this end, really what sets the properties of that ice are the processes of solidification of a binary alloy, and that's what I'm going to talk about here. So really I'm going to sort of intro how you get up to 2.5 meters, and then from there on it's a lot of mechanical forcing. And just to put this picture up from the very beginning, when you form ice from a solution which has some impurity in it, in the case of the ocean it's about 3.5 weight percent, mostly sodium chloride, you form what's, at least in the literature, called a mushy layer. It's a porous medium. It's got these ice crystals. You can see for ice it forms this elongated crystal with the c-axis pointing in one direction, and it's porous. It's got a liquid fraction of enriched interstitial brine, and the crystals themselves are essentially pure. There's some interesting features here already that you can see with the length scale set by the centimeter scale over here, and we'll come back to some of these features called chimneys later in the talk.
What view am I looking
so
at?
this is looking at the underside of some sea ice that's been grown in the laboratory.
So gravity is this way.
So gravity is pointing down out of the board. We're looking straight up at the ice that's just grown.
So these icebergs we talked about, they're usually enormous. This is not part of this. This is
no. So the icebergs are formed on land from more or less pure water, and then flow down and are deposited on the ocean. Whereas this is ice which is grown from cooling the ocean surface, and where salt plays a very important role in the properties and the dynamics of the ice that's formed. So just to stress that point a little bit further, if I can get the slide to progress. There you go. All of the properties of sea ice that one cares to model, the specific heat, thermal diffusivity, latent heat, the density, all depend on, if you're going to talk about these properties on a length scale larger than this crystalline spacing, they depend on the phase fraction, the fraction of essentially pure water ice and the interstitial brine. And it's important when you talk about the thermal fluxes going through sea ice, because the phase fraction can vary as a function of height. So the most fundamental part of modeling these kind of solutions as you solidify them is the binary eutectic phase diagram. So on the vertical axis, this is the temperature. On the horizontal axis is the concentration of impurity, in this case salt. And of course you see that for a pure solution, you freeze at 0 degrees. But as you increase the salt concentration, the freezing point goes down. If you take a parcel of salt water, so of ocean salinity, around 3.5 weight% of salt, and you cool it past this salt-dependent freezing point, you form ice, which is, in this case, idealized as pure. It's essentially pure, nearly complete rejection of the salt, and you have an interstitial brine, which is enriched in salt. If you cool that material yet further still, past the eutectic temperature, you form a eutectic solid, which is a mix of both ice and salt crystals. And for much of what I'm going to talk about, I'm actually going to use an analogous system, which is a little bit easier to experiment with in the laboratory, and that's a commonly used ammonium chloride solution, which has been used to study these mushy layers. And here's a picture of that ammonium chloride mushy layer. It's useful to use in the laboratory because for 28 weight% ammonium chloride, you can freeze it at room temperature, and so you can not have to worry so strenuously about insulating from room temperature. But you can see that on this side of the eutectic phase diagram, as you cool this solution from below, you start to form these salt crystals of ammonium chloride, and these are bathed in an interstitial fluid, which is now relatively fresh. And immediately you can see that on a length scale much larger than this interdendrite spacing, which is about 0.5 millimeter, you can average this thing and come up with a porous medium. But this porous medium is now reactive because the crystal to brine fraction is set thermodynamically by both the temperature and the local concentration. So here we have a cold base going up to a relatively warm bulk solution, which means that you solidified out most of the salt at the bottom. You're left with essentially fresh water going up to saltier water. And already you can see that this is going to lead to some buoyant convective instabilities where you have a porous medium in which you have a buoyancy gradient effect, or a salt gradient, leading to buoyancy within this porous medium. So to look at that problem further, typically what's done in the sort of the metallurgical and in some of the sea ice literature is to look at the following problem. We take a bulk solution and we pull it through a fixed temperature gradient at a speed v, and that means that we can achieve a steady state in which we have a lower boundary here given by that eutectic temperature where you crystallize out both ice crystals and salt. You have this mushy region, which is this porous, reactive porous medium composed of all those, in the case of ammonium chloride, salt crystals. In the case of sea ice, this would be water crystals, capped at the top by the liquid's temperature at bulk concentration, or thereabouts, and then an overlying liquid above. And the equations that describe this averaged over several of those interdendrite spacings are as follows. So in the liquid above, you're really looking at advection and diffusion of both heat and concentration, and the Navier-Stokes equation describing momentum. In the mushy layer below, you have advection and diffusion of heat, but now you have to worry about the fact that that phase fraction can change throughout this mushy region. And so there can be release of latent heat internally as you change the phase fraction. Similarly, you have a equation conserving solute where I've neglected diffusion, as is typically done because the length scale there is so small. But again, you need to worry about the release of solute as you change the phase fraction within this porous medium. And then velocity is governed by a Darcy's law.
So if you just stop there, this should put everyone now at ease because of what Amy spoke about. So now all Amy has to do is to take this plus boundary conditions 13th order system and put in the mechanics of the ice.
Exactly.
And then predict it. So you're in business for years. Yeah.
So what about the transition between the two? Continuous? Is it continuous?
So the transition between the two, if you formulate it in this particular way, doing two distinct regions, you then have to worry quite a lot about exactly what the boundary conditions are matching.
The free surface then. Somehow.
So you have a free surface in which you match things like velocity, pressure, stress, fluxes of heat and solute, and then you have to make an assumption about what the gradient between temperature and concentration are in the liquid right next to the solid. And typically what's done is to assume that there's no what's called constitutional supercooling, so that essentially it's relieved all the constitutional supercooling ahead of those crystals.
Mm-hmm. Mm-hmm.
So if you think, if you're familiar with the Mullen-Sakirka type problem, this is sort of, if you grow crystals with a solute gradient, you can get a case where because the diffusion of heat and solute are different, you actually have a region in front of a planar interface of solid and liquid where the temperature is below the freezing point because of the solute there. And this relaxes that condition. This is essentially those dendrites growing out to a saturated position. So now if I take that sort of steady state system and I look at properties, steady state properties in front of the this mushy layer, what do they look like in the liquid? Well, there are three length scales that really govern this system. One is a thermal length scale, which is simply the thermal conductivity or diffusivity divided by the growth velocity. There's a much smaller length scale, which is the diffusivity of the solute divided by the thermal diffusivity times the thermal length scale. So that's really the length scale over which composition diffuses. And a much longer length scale, which is given by the Prandtl number, ratio of viscosity to thermal diffusivity, times this thermal length scale. And that's much greater than the thermal length scales. There are also two Rayleigh numbers in the system. One is given by gravity times the thermal coefficient of expansion, temperature difference between the interface and infinity. This length scale cubed, thermal diffusivity times nu, and a compositional Rayleigh number where instead of alpha delta t, it's now coefficient of compositional expansion times delta c. We can solve sort of a steady state version of the temperature and solid fraction within this mushy layer, and of course you get essentially what you expect. It's cold at the base of this porous medium, and it rises to the liquidus temperature at the top, and the solid fraction varies with depth. So it goes to 0 at the top, and it increases as you go towards the base. And so there are a couple of non-dimensional numbers that really characterize this kind of system. One is the compositional ratio, which tells you how much solute you release as you change the phase fraction. The Stefan number, which tells you how much latent heat you release as you change the phase fraction. There's Darcy number, which is the non-dimensionalized permeability of the system. And a porous medium Rayleigh number, which now has delta C, the compositional forcing, the permeability in it, times the length scale divided by kappa nu. So three Rayleigh numbers that characterize this system. And then these other parameters, the compositional ratio, Stefan number, and the Darcy number. So doing the next sort of step in this kind of system of 13 PDEs, you get the following linear stability analysis. So here I've plotted the porous medium Rayleigh number versus a wavelength doing a typical linear stability analysis. This was first done by Gray Worcester in 1992. And as is typical, this is the neutral stability curve separating stable regions from ones which are unstable. And you find that there are two modes of convection in this system. One is this long wavelength, short width, small wave number, mushy layer mode. And one is a small wavelength, large wave number, boundary layer mode. And so what do these two modes look like? So if you look at the mushy layer mode, this is really convection in a reactive porous medium overlain by an infinite liquid, or a semi-infinite liquid. You get streamlines here where you get fluid motion throughout both the porous medium and the overlying liquid. And the boundary layer mode where essentially you get convection only within the liquid. What's happening here is you're growing up this dendritic array. You have diffusion of composition in the liquid ahead of your reactive porous medium, and that gives you a very small length scale, the compositional diffusive length scale, over which you get this kind of boundary layer mode of convection. And as you solidify those crystals, you're also developing, in the case of ammonium chloride, a very fresh fluid both within the interstices and within that liquid layer, leading to a much larger length scale of convection.
You haven't mentioned about the equation of state of the liquid, what dominates the density?
So in the case of both seawater and in this kind of system, ammonium chloride, it's composition which really dominates convection. So really, in both the overlying liquid and within the porous medium, it's variations in composition which really drive fluid motion. So if we look at that in a laboratory system, here is a Healy-Shaw cell, so a very thin cell, about 1 centimeter wide, where I've put in 28% ammonium chloride, and I've turned the temperature down at the base of the cell. And what we're looking at is something called synthetic serum. It's a way of essentially taking a qualitative look at what the density of your solution is. And what you see initially is, as you turn the temperature down at the base, you see a cold thermal boundary layer growing at the bottom of the tank. As time progresses, you begin to nucleate crystals at the base, which are still small enough that we're not really seeing those crystals. But the fact that you're solidifying some of that salt at the bottom of your tank and releasing this relatively light, fresh fluid gives rise to these small plumes coming off of those growing crystals. As time progresses, this forms a fairly turbulent boundary layer mode of convection.
What's your... Sorry.
There is one takes this 28% ammonium chloride. That's not what we want to learn about Earth, water, but on other planets with different compositions, or just was it easy to model? Or?
So the argument would be that if you're growing 28% ammonium chloride in the laboratory, because it's simply easier with that particular phase diagram, you grow it from below and you release this essentially fresh water that wants to rise. And it's dynamically exactly the same to switching everything around and growing, say, water with impurities, cooling it from above, and having salty fluid rejected between the crystals and draining out of that network. So the ideas here are essentially flipped around from what you'd think of in the case of oceans being solidified on Earth, or in the case of some of these icy planets, if there were significant on the percent level of impurities within that part. So you're at, yeah, so in the case of, yeah, so this is sort of the very small scale, in some sense, precursor to that. You form these large areas of ice in the polar oceans where you cool the top, you form the ice, and through you drain the salty and very cold water out of the ice as it forms. And that therefore gives you a very dense pool of water to really initiate thermohaline circulation. The exact connection between the two is, I think, in terms of where exactly that downwells and that sort of thing, I think is a larger scale geophysical question which is not completely closed yet. But certainly the processes are definitely tied.
I mean, if you were on some other planet though, and the equation of state wasn't dominated by composition, then this analogy might be problematic. But it is certainly dominated by composition for salt, water, and ambient temperature pressure.
Yeah.
Could you say a few words about the technique of synthetic Schlieren photography? Are you basically integrating the radio transfer equation along the density profile, or how does it work? Or something simpler?
So it's actually a fair degree simpler. It's a lot like particle image velocimetry. What you essentially do is you've taken a dot pattern and you've placed it behind the experimental apparatus, and you take a picture. And whenever the concentration or temperature changes in your apparatus, it changes the refractive index.
Yeah.
And so those dots appear to shift. And so essentially this is an image of the experiment with here a thermal diffusive boundary layer minus the reference image from the beginning. And that gives you the qualitative sort of density difference between what's happening in your experiment now and before you start the experiment. To actually work out the density differences themselves is a little bit trickier.
I mean, it gives you, that's index of refraction. You would have to calibrate index of refraction against density to get actual density and mixing and training and so forth.
Is there a simple formula that you could write down, or is that not that simple?
Not off the top of my head.
No. Okay.
So just to show that if I take this experiment to longer times yet, here you're starting to see those crystals at the bottom of the frame with this boundary layer mode of convection. And then jumping a fair bit further in time, here's this reactive porous medium, this mushy layer, with a very dramatically different style of convection emanating from the top and at yet another later time. And that style of convection is dominated by these thin plumes originating from localized patches within the ice. And so the flux of in this case, fresh fluid from the ammonium chloride mushy layer, or in the case of sea ice, the flux of salt from that sea ice mushy layer is dominated at later times by these plumes. So if I show a movie of this process, here's a tank in which we cooled from below. You initially get this mushy layer that forms, and you get a boundary layer mode of convection which rapidly goes to this mushy layer mode of convection, in which you get these thin plumes rising from this reactive porous medium. And maybe if I start again, we'll get a longer shot at this boundary layer mode of convection, which is defined by sort of double diffusive style convection, leads to this mushy layer mode of convection in which fluid motion penetrates deep within this porous medium. You get these narrow plumes arising from these regions of zero solid fraction. So this is where you first really start to see the effects of this reactive porous medium. As soon as you start driving flow within your crystal network, you're advecting temperature, you're advecting salt, and that can give rise to regions where you've entirely dissolved the crystal fraction.
This was the actual speed?
No, that's speeded up quite substantially.
Yeah.
I know that the movie is actually about, so this experiment would take about 3 hours to run. So in sea ice, what typically happens is you can characterize the convection in the following way. If you imagine in sea ice a lead opening up in the wintertime, you expose ocean water to a very cold atmosphere, you begin to solidify. As you initially solidify, the depth of that ice is so thin that the characteristic Rayleigh number for that reactive porous medium, that mushy layer, is very small, and you only get this boundary layer mode of convection, which is again that sort of convection in the compositional diffusive boundary layer ahead of the ice. Once it's grown to a critical thickness, HC, you can achieve a critical Rayleigh number, again given by this sort of combination where the permeability and this critical height play a key role. And once that critical Rayleigh number is exceeded, you can actually get this convection within the ice, and that dramatically changes the phase fraction. As we saw before, you get these chimney-like structures, which are regions of zero solid fraction. So for ammonium chloride, you can imagine that these form in the following way. You're cooling from below, and it's relatively warm above. Therefore, you're solidifying out more salt crystals at below than at above, and so the interstitial liquid is relatively fresh at the bottom and relatively salty above. If you take a parcel of fluid in this reactive porous medium and you loft it higher up, you thermally equilibrate that parcel of fluid fairly quickly, but compositionally, to reach equilibrium, you need to dissolve some of the surrounding crystals. And so upwellings with an ammonium chloride much later lead to dissolution of the matrix, and so give rise to this zero solid fraction chimneys. Downwellings, correspondingly, you're bringing relatively salty fluid into a cold environment, and so you're solidifying and you're clogging up the network. You can reverse this argument exactly in sea ice, turn it on its head, and there, if you take salty fluid and you drop it down, you start dissolving some of the pure ice crystals. Whereas if you upwell salty fluid up towards the colder surface, you start clogging the network by solidifying out some of the water. And this is tantalizingly hinted at from the linear stability analysis, where those flow patterns in the mushy layer mode of convection, where you get upwellings in the middle, you're advecting temperature, and so it's cooling and warming in the downwellings. But more importantly, when you're upwelling in the ammonium chloride system, you're starting to dissolve some of the matrix, simply because you're taking that concentration and injecting it through this reactive porous medium. And conversely, in the downwellings, you're solidifying some of that system. The boundary layer mode, in comparison, because your streamlines barely penetrate within this reactive porous medium, have a much smaller effect on the porous medium, and so don't change the solid fraction appreciably. These contours here are about 10 to the minus 3 times the contours on the previous plot. So when you solidify a binary alloy, you tend to form these porous medium, this reactive porous medium, and as you move fluid throughout that reactive porous medium, you can dramatically change the phase fraction. And now what I want to do is turn on an added complication, which is looking at systems in which you have externally forced fluid flow. So in the ocean, that would be ocean currents. In the Earth's inner core, you have convection in the liquid outer core that's causing shear across this growing mushy layer. And in all cases, that can affect the sort of dynamics and the evolution of the phase fraction of this porous medium. If we take an external flow of varying strength past one of these mushy layers and conduct the same sort of linear stability analysis, we can make a plot again of the Rayleigh number versus the wave number, and we see that initially it stabilizes both these boundary layer and mushy layer modes of convection. But as the flow is increased to yet higher velocities, you can start to destabilize first the boundary layer mode and then the mushy layer mode. And so if I now track the minimum critical Rayleigh number for both the mushy layer mode, this long wavelength instability, and the boundary layer mode, this short wavelength instability, we see that as you increase this critical, or as you increase the strength of the external flow field, you can actually force changes within the ice liquid interface, and also within the phase fraction of the ice itself by forcing both the boundary and the mushy layer mode of convection. So by applying some of these external flow fields, either due to oceanic currents or other processes in other settings, you can also alter the sort of dynamics of these porous medium. And one can think about it in the following way. If you have a mushy layer which is thrown from below and you apply a strong external field, any corrugations of that mushy layer liquid boundary will have this compositional diffusive boundary layer ahead of it. And the flow field, the external shear, will actually perturb that flow field and act much like sand ripples and cause a differential growth rate in the interface. So in the boundary layer mode, if you apply a strong shear, you end up having these traveling wave solutions on the interface of this mushy layer liquid interface. At the longer length scales typical of the mushy layer mode, the interaction is slightly different. Again, you have this external shear flow interacting with topography on the mush liquid interface. And here, as you apply a strong external shear flow, you generate essentially a Bernoulli pressure difference between the peaks and the troughs of this interface. And that can essentially force flow within the underlying porous medium. So now you have a mechanism in which natural buoyancy doesn't have to drive that convective flow. You can force it by an external fluid flow going over sort of a corrugated ice liquid interface. And the effect is essentially the same as what you saw in the case of natural buoyant convection. When you have this flow going over this corrugated ice liquid interface, you have streamlines where upwellings correspond to the peaks, downwellings correspond to the troughs, and this leads to cooling underneath the peaks and warming underneath the troughs. But more importantly, cooling underneath the peaks and warming underneath the troughs, but more importantly, this leads to dissolution of the matrix. And so you're changing the phase fraction again by forcing flow within this mushy layer. The ultimate sort of fate of which is likely to give rise to these regions of zero solid fraction. Here, of course, you've broken the symmetry by applying a shear flow from left to right. So instead of these point regions of zero solid fraction, which we saw in the buoyant convection, you get these planes of zero solid fraction aligned perpendicular to the external shear flow. And as is the case with buoyant convection, everything depends critically on the permeability. And here, because you're forcing with an external flow going over these perturbations, it depends critically on this critical Darcy number. So here I've plotted three curves of critical Rayleigh number here versus the strength of the external shear flow. If you essentially turn off the external shear flow, you get a critical Rayleigh number, which is basically the buoyant, natural buoyant Rayleigh number. But as you turn on this external shear flow, its effect is much greater for much more permeable matrices than it is for matrices with a much smaller permeability or a smaller Darcy number.
But there's nothing about this that would say it wouldn't happen in anything like liquid metal, for example. Is there something particular about these three Darcy numbers here that is only relevant to ammonium chloride or ice? Or
there's nothing particular about these three Darcy numbers. These three are the magnitude of which are chosen for the system, the ammonium chloride system. But in terms of the analysis, these are all sort of appropriately non-dimensionalized. So they apply to liquid metals, they apply to ocean salinity, waters. You'd need to, estimate what the critical or what the Darcy number is of those particular media. So you can also do some experiments on this kind of system, and I've done some of those experiments for my PhD thesis, in which we took a flume with a cold plate, and this enabled us to apply a shear flow through the flume by introducing fluid on the left and having it flow over this test section or cold plate and being collected in this reservoir at the back and recycled to the front. And essentially what we did was to grow a mushy layer of a particular thickness off of this cold base plate, and then look at the stability of that mushy layer to a shear flow applied over the top. And if I show a movie now looking down top view onto this mushy layer, we see this following type of behavior. So fairly uniform mushy layer viewed from below, the shear flow will be applied from left to right, and we see this pattern of dissolution aligned roughly perpendicular to the applied external shear flow. The base plate of this tank is painted black, so what we're seeing are the crystals being dissolved, and you're seeing the base plate through this crystalline network. And as we turn off the shear flow, everything grows back in, and you get this sort of smooth mushy layer again. So again, this is a way in which, using an external shear flow, you can change the phase fraction of this sea ice, or in this case of ammonium chloride, just by applying a strong enough shear flow to the system to force fluid flow within that porous matrix.
But the mushy layer is really ending here, is it not?
So we're looking straight down.
Oh, I see. Sorry.
It's growing out this way.
I see. Okay.
And then we're applying the shear
Yes.
flow off.
Yes.
Yeah. And just to sort of show that you can make some sense of this theoretically, this is the Darcy number versus the strength of the external shear flow, and the blue curve here is this linear stability analysis, dividing when you'd expect to see this sort of dissolution pattern from when you'd expect it to be stable to relatively weak shear flows, and to within one adjustable parameter, which is the dimensional permeability of this matrix. It's fairly unknown experimentally. You can certainly get a fairly good agreement between when you'd actually force changes in the phase fraction to when it's stable to this external shear flow. So one application which is a little bit more interesting from a planetary scale and a more remote mushy layer kind of perspective is the following observations. So if you look at the underside of sea ice, again this underside of laboratory grown sea ice, where you can see both these chimney structures where convection within the sea ice has dissolved the matrix and led to these zero fraction chimneys. Well, again, you notice that the crystalline pattern of ice grown from salt water is to have these essentially platelets that grow down from the ocean's surface and have a long axis and a short axis. And what's been noticed in the 80s by Weeks and Gao is that if you look at the north shore of Alaska and measure, taking a series of ice cores, you measure the direction of those crystalline platelets. They're all aligned essentially perpendicular to the external shear flow. So here are the best estimates of the oceanic currents that flow along the north shore of Alaska, and then on these stereographic plots, the sea axis, and they're clustered around perpendicular, or they're clustered around this oceanic prevailing current. And what might be interesting about that in the case of the Earth is that you have this case where at the core of the Earth you have a solid iron core that's surrounded by a liquid iron shell that's convecting rapidly due to the compositional convection. That compositional convection is organized roughly in a series of Taylor columns by the Earth's rotation. And so that gives a predominant direction to the flow around the Earth's inner core. And so if there's a mechanism much like what's found on the north shore of Alaska, this style of flow may align the iron crystals and gives rise to an observed seismic anisotropy. So if you take a seismic wave off of an earthquake and it travels through the Earth's inner core, it travels about 3% faster going north to south than it does east to west. And one possible explanation of that is to invoke the alignment of iron crystals in a manner that's similar to the alignment of sea ice crystals. So this gives an interesting way to look at both solidification and fluid flow remotely using, in this case, seismic techniques. And to sort of put a plug in for David's talk, there's also been some work by people like Christopher Krems at the University of Washington where they looked at spatial patterns of colonization of sea ice. You can imagine that these pore spaces within sea ice provide some of the habitat for biology within sea ice. And so perhaps these sort of interactions between shear flow and topography can lead to spatially distributed patterns of colonization within sea ice.
What are those things?
These are ice stalactites. These are essentially, you have a chimney, one of these regions of zero solid fraction, pumping out very cold water. And as that cold water descends, it cools the surrounding ocean water and forms these long stalactite type formations that can reach up to meters down into the ocean below.
Well, David is the expert on all this, and we're going to hear a lot more about it. But I just want to say that from the large scale of the biological part of the problem, there are shrimp. They're called under ice amphipods. You're not going to say anything about amphipods, are you? Maybe you will. Okay. So the first time, so this picture I think is taken by Jamie Morrison with his an ROV, and the very first, he has this thing that drives around underneath the ice and takes pictures, and the first time he looked up into one of these things, out comes a couple of shrimp. Right? There are 4 types of amphipods in the Arctic that live there. But the reason people in Scandinavia study these things intensely is because they are the food source for polar cod. And so in the Barents Sea, when the ice melts, since these shrimp can't swim very far, they're the food source for the polar cod. And so at the ice edge, there's an enormous amount of activity because the cod are eating the shrimp, and the seal are eating the cod, and the bears are eating the seals, and so on and so forth. But the thing you notice here is that there's green stuff, and that there are these big holes. I don't know what that picture is up there to the right, though.
The picture on the right is off of Christopher Krem's website, where he's taken some images of various organisms growing within sort of small spaces within sea ice.
Is that it?
Mm-hmm.
Oh, thank you.
So in freshwater it's completely different then?
In freshwater it's completely different because you don't have this salt basically controlling the nature of solidification.
So the temperature of maximum density depends on salinity, and so there is a transition. So if you cool the water from above, pure water has a density maximum of 4 degrees. So you can convect so far, and then it will start to freeze. Whereas salt water, or ocean water at least, that is moved to a lot lower value. So you can mix up the water column by cooling it before you freeze it. So the upper part of the ocean that has ice on it is a lot different than the upper part of the lake that's frozen. And a lake that's frozen, you can't see these things that Jerome pointed out, these holes and these fissures that form due to compositional convection. In fact, there's very little such structure. And moreover, and you can figure this out over lunch, the C-axis, the crystallographic C-axis of the sea ice is this way, and the crystallographic sea ice of lake ice is this way. entirely perpendicular. I'll buy coffee for anyone who can figure that one out.
Does the growth velocity, isn't it? We revert this because here you have another driving force, the concentration field. So it must be just the, or you must in the case of lake ice, you grow mostly in that direction, and when you grow in that direction, that's why the sea ice affects. Is that right?
It's close. So certainly, if you cool the surface of fresh water, then what you're getting at is the fact that ice grows a lot faster in the direction that's perpendicular to the sea axis than parallel to the sea axis because of a roughening transition. So if you put one crystal on the surface of a lake that's cold, and it happens to have a sea axis like this, then it will grow very rapidly over the surface. But in the case of the salty water, there's this instability, and that instability gives this fingering, which makes the fast growth direction here. There's a little more involved about it, but okay, I owe you coffee now.
But it's free anyway.
Yeah, I owe you a beer.
So the growth term that causes the growth of the mushy layer is really described by the dphi by dt. Is that what it is? Which is what you, and that was an imposed temporal profile. Is that correct?
So
you
the
go
growth,
back to the one of the first equations.
Yeah.
And your page 3 or something. I don't know which one. Then you had the set of equations for the liquid and the Darcy faces. Yes, here.
Mhm.
So it's the C times dphi by dt, which is the growth of the mush, right? Is that correct?
Well, so this is describing internally the change in phase fraction within the mushy layer. The actual growth of that mushy layer is on the longest length scales is forced thermally. So you set up this thermal field which gives you the growth of the sea ice. The changing phase fraction is determined by this release of latent heat and the release of solute.
It's important to say these are homogenized equations, right? So you do the mean field theory over length scale, which is large relative to the intracrystalline spacing. So that phi is just the volume averaged solid fraction. So you can think of these as, you know, equations for a sponge that's saturated with water that you freeze, and those are just sources of latent heat,
Yes.
sources of
So, but if you want to grow the layer, you have to mess around with this profile. Is that correct? The spatial and temporal profile of this. Or how would you make the mushy layer thicker? I mean, what determines the spatial extent of this mushy layer in the framework of these equations?
In the framework of those equations, what determines it is essentially the temperature you apply, the temperature gradient you apply, and the far field concentration.
So then the growth is self-consistently described within those equations you're saying.
And then given those two,
Oh, I see.
you then can construct what the phase fraction looks like as a function of depth.
So then it depends really on the boundary condition that you have between these two phases. Yeah?
strongly, yeah. So they're very so temperature. You've got if it's a classical Stefan problem, you've got a temperature at the boundary, and then at the mush liquid interface, you've got the composition dependent temperature. So for the ocean, you know, -2 degrees Celsius for ammonium chloride, it's around room temperature. So that's for the temperature only, and then for composition, it's a little more fiddly. But you could also have a condition which constrains the gradient of the temperature to the gradient in composition, which is what Jerome was talking about, and so forth. But there's an additional condition for any moving boundary problem, which is the Stefan condition, which is energy conservation, right? Which says that the rate of motion depends on the temperature gradient in this mush, and the temperature gradient in the liquid. So that's an auxiliary condition to get the motion of the boundary. But in the way Jerome sets up the problem, he cheats in part because the it's not a time-varying motion of the interface, it's a constant value because he's set it up and takes the system, so that's not what the ocean does. He takes the system and puts it on a block of copper, which has got an imposed temperature gradient, and then just drags it at a fixed speed. Okay, so there's still a step-on condition. It's just that it's a constant speed rather than a time-varying speed.
And purely for the reasons of a linear stability analysis, having a base state that doesn't vary with time.
And numerically, how do you solve it? On a mesh? I mean, how do you do the free boundary between the two?
So numerically, I will say I haven't solved it numerically in the full nonlinear sort of sense, but there are different ways one can imagine doing that. One could either do your mesh with a boundary condition in here, or more recently people have done something called the enthalpy method, which you're essentially tracking enthalpy throughout the whole system. And there you can actually work out the interface a posteriori just by interrogating your variables. So in fact, it recovers this kind of formulation without the necessity of having this matching interface. So I think that's computationally one of the easier ways to do that.
Yeah, but it has problems. I mean, it misses well-known features as well. And it's not just due to grid size, it's due to physics.
Yes.
Right. Yeah. So, but in fact, you still solve these equations numerically to do the stability analysis and get the stream functions and so forth.
But the linearized versions of these.
The linearized version of them. So now that you're standing there, you can be. So how come these fissures don't? Or maybe these fissures occur on Europa. Maybe they're occurring on Enceladus.
So I mean, certainly on a place like Europa, you'd imagine that for some region at the inner ocean ice interface, there's going to be some region in which there's a phase fraction variation, if there's any appreciable concentration. Where that decays off to a value in which the phase fraction is so low that the permeability is negligible, I don't know how deep that'll be. But certainly, if constant composition plays a role in those oceans, you'd expect some region in which you'd have mushy ice at the bottom.
I mean, I guess to my mind, we can ask Amy, but if that ice grew from that ocean, everything you've told us is independent of anything except for the fact that you have a binary phase diagram. So okay, it's ice, but there's salt. So if you could treat it in this way, or even in a more complicated way, if that ice grew from that ocean, it has to have gone through one or a number of these processes. So it may be that these two-layer models that people make are fortuitously right in the sense that there could be a mushy layer region which is very active at the bottom of the ice that's on Europa or Enceladus, and an upper layer which is not so active.
Yeah.
But has anyone, I mean, what's the initial value problem for the ice cover? You don't know? Yeah, we don't know.
Does that work out with the salt concentration? If you produce 100 kilometers of ice, you have the concentration below this watery region must be very, very high.
I mean, I've actually never simply, you could just apply the Lever rule and see what happens, but I've never done it.
Because in the earth, in the ocean, if you grow 2 meter layers of ice, you do not change your reservoir.
Precisely.
Yeah.
Precisely. Yeah. I don't know. I mean, of course, it depends on it depends on how much you put into the ice, and that's really important because it's not unique, right? I can conserve total number of salt molecules in my system as I grow the ice, but whether they're in the ice, in this mushy layer, or in the liquid, that's not obvious. So, for example, if you grew the ice in such a way that the critical porous media radius number was never exceeded, then it's always inside of the ice, and it's more like salt in an ice sheet in Greenland, if you did, then you're always going to be getting rid of the salt, enriching the reservoir, as you say, and then it's very salty, and the ice has zone refined itself, which is what you'd like to do in semiconductors, for example.
Well, I think the other important thing is that if salt does play an important role in those kind of scenarios, then the convection that you get in the ocean would be strongly influenced by a rejection of salt. Just because, as is the case in these sort of systems, the coefficient of expansion for salt is much greater than it is for temperature.
Yeah, I mean, I think it is the combination of those two things is extremely important. In fact, essential in understanding why is the ice as thick as it may be on a place like Europa or Enceladus, because to get rid of the heat, I mean, let's think of the Earth's core, right? There's the inner core solidifying, releasing buoyant residual, and then there's high radiant number convection in the liquid metal core, and that heat's being pushed up through the mantle of the Earth. The nature of that convection is crucial in the growth rate of, for example, the inner core. In the same way, if you go to the ocean, if you go to the real Arctic Ocean today, the picture that Jerome showed of the thickness distribution, it's really 3 meters because that was draft. The mean thickness of the ice is 3 meters, and it turns out that's a pretty good. That curve is pretty good. There's an interesting theory, which is a Fokker-Planck sort of equation, which describes this, but that's an observation from submarines. So pretty much wherever you go in the Arctic, 3 meters is the mean thickness. And if you change so the heat flux from the ocean to the underside of the ice is this huge ocean, deep 3 kilometers, 4 kilometers deep, and a 3 meter vernier, which is a biologically active vernier sitting on the top of it. If you change the heat flux, which is already very small, by factors of 2, the amount of ice changes dramatically. So that's a calculation. We've seen things in the literature and in reality about how much ice has melted in the Arctic in the last couple of years. But to give you an idea of numbers, 2 watts per square meter, okay, is the heat flux coming from the ocean to the underside of the ice. If you make it 0 in the state-of-the-art model for how the ice grows, the ice basically becomes 8 meters thick, which is not an observed quantity. And if you make the heat flux something like 6 watts per square meter, all the ice goes away. Okay. All the other fluxes in the energy balance, the radiative fluxes at the surface from the sun and so forth, are hundreds of watts per square meter. This is 2 orders of magnitude smaller, and yet the ice is the most sensitive to it. So it's the convection that's really essential. So how convection would operate in these environments of these icy moons seems to me to be very important in the liquid, not only in the in the actual ice like Amy was talking about, but in the liquid.
So did you say that when we see these things about how the glaciers melt, it's always case where it's not water beneath, it's on land? Because and when water is beneath, it's very insensitive to changes in the atmosphere?
No. So what I'm talking about is the sea ice. So last year, the aerial coverage of sea ice, we could probably, if you have a web connection, you can go to cryosphere.com, and you can compare the ice cover. That wouldn't be a bad thing to do. No, it's because this ice that grows from the ocean is so thin. It's very sensitive
to the ocean,
to the climate, but in particular, the most sensitive variable is the ocean, because because of this boundary condition.
Okay, so
yeah.
the climate change, when I think of it, is sort of the atmosphere, it gets warmer or cold in the atmosphere, but we're not also talking about the heating from the
Oh,
ocean.
in fact, you can make large changes in the atmospheric forcing, and the sea ice won't change very much.
Yeah.
And the reason is because there's a rectification because of the Stefan-Boltzmann law. Because it's always radiating out at sigma t to the fourth, and there's a balance of fluxes all of order 100 watts per square meter. And when one changes by a factor of 10%, the other adjusts, and since you have this sensitive radiation boundary condition for temperature, it doesn't matter. You can change a fair amount. What does matter is the aerial coverage of ice, because the difference in the absorption of solar radiation in ocean versus ice is enormous. The spectral albedo of ice is very high, and therefore, if you change the aerial fraction of ocean slightly, you increase the amount of heat input to the ocean, which is delivered right back to the ice and melts it.
So the changes that actually occur in the heating from the ocean,
it's extremely important.
So this is going to be self-generating process then?
In part, and a crucial aspect of this is this thermal haline circulation, which is driven by solidification. So, this lasts about a year ago, right? Was the minimum ice cover, and the previous minimum was 2005, and this minimum is a larger loss by like the area of, I don't know, California and Alaska put together than the previous minimum. But this year, it hasn't. If you look today, it won't be anything like this.
It's coming close to this ice.
Is it?
There's more ice this year, but it's still coming close.
Yeah. See now this year you grow, because you lose more ice. You have to grow more thin ice to recover, and that thin ice is more sensitive to mechanical deformation than the thick ice is.
Isn't there another variable coming? I mean, when you have this melting going on with a fresh...
So it stabilizes...
It's changing the concentration on the surface.
Precisely, yeah.
So for a transitional period, you change your boundary conditions again.
Precisely. So there is a prediction made by someone in this room about exactly that issue. So if you melt a little bit, in fact, there can be a period over which you stabilize the upper water column to this convection. And the question is, what's the transition? So if you go down to the lower left of that, all the way down, keep going, there, compare side by side. So we can compare today with 1980, compare it with a year ago, after they loaded.
The white here, is that the ice, and the purple is...
So the purple is just, comes from, that's a false color scheme for ice concentration.
Minimum, yeah.
Well, that's just the ice concentration.
So if
that's
you
the
take
aerial.
like leads and broken up ice would be...
So you see
So all of this stuff is 100% ice, but along the ice margin, you'd have some
you
blocks
see
of ice.
the concentration goes down to 40, down to 0.
Yeah.
Okay. So this is from microwave. It averages over, I don't know, the footprint of this is like 100 kilometers square. But okay, so on the left, a year ago, was about the least area of ice cover during the satellite era. Okay, so all the purple stuff is the floating ice that Jerome was talking about, and that's yesterday on the right. So, I mean, 2005 was less than this as well.
Yeah.
Yeah.
Well,
which was the previous minimum before 2007. But the real, so there's this thing that people talk about called ice albedo feedback, and the ice albedo feedback is just that the amount of white stuff on the surface of the Earth is important for reflectivity, but in particular where you have ice next to water, as opposed to, say, on Greenland where you have an ice sheet, where there's ice next to water, then there's this absorption of radiation which heats up the water and melts the ice. apart. But that flux, the boundary condition between the ice and the water, is the one that the ice is the most sensitive to.
What is the difference between the ice surface area in the summer, the minimum and maximum in a year? And how much is?
It's about 8 million square kilometers of growth during a year.
Do you know how big this is?
It fills in everything. It fills in all the. Yeah, just find a maximum. So you have ice down in the Barents Sea, and you have ice in the Bering, and ice in the Sea of Okhotsk, and ice in Hudson's Bay, and so on and so forth. So it's a huge it's a huge factory of salt.
Yeah, I mean, for reference, it's these sort of areas here that are thought to be sort of the areas where you produce that cold, dense water that then leads to the thermohaline circulation. So it's at least correlated with where you get these huge areas of solidification of the sea ice.
I mean, the thing to probably say about this, the large scale importance about this salinity being driven into the ocean from the salt, from the ice growth, is that if you go and observe the water in the Arctic and measure its temperature and its concentration, what you observe is that because the equation of state depends on the salt, that there is this hot water, I mean literally hot, 2 degrees Celsius, between 1 and 2 degrees Celsius, about 300 meters below the surface of the ocean, but it's trapped by the stable salinity gradient. So that's what's this little heat flux, which is 2 watts per square meter, leaking up through this stable salinity gradient. So the idea is that when you melt back a lot of ice like you do in the summer, if it was anomalous like we did in 2007, then the next year you have excess growth of thin ice, which is excess production of dense salty water, which could erode away that stable stratifications and bring up that heat. And if you just do the energetics of it, you find that there's enough heat stored in that layer which is trapped there to melt all the ice in less than a season. And so but we don't even know where does it come from. Where does the stratification come from? Why is it stable? There's no good first principles understanding of where that comes from. But it's certainly the case that if you bring that heat to the surface tomorrow, it will melt the ice, no matter how cold it is out in the atmosphere, or how dark it is. There's an enormous heat reservoir there. Seems like it's time for lunch.
Last remark, I think here, what you've shown is that you were asking if there's something, an equivalent in the solidification of binary metals.
Yeah.
I think there's an equivalent for what you're looking at in electrochemistry with binaries. There you can reduce sort of an equivalent of these mushy layers by eroding one of the 2 components by changing the other potential. And you get patterns like that.
Mm-hmm.
You mean like electrodeposition, that sort of thing, or?
Yeah, or the other way around. If you start with a smooth surface and you change the potential and you take out one of the 2 components, the same thing. You have a concentration gradient.
Okay, so there's a diffusive instability.
Yes.
Okay.
And it's producing patterns. It's producing sort of mushy or porous
Yeah.
layer.
Uh-huh.
If you have flow, I guess you could
control
pretty much the same you're doing with the ice.
And has there been sort of a phase field model made of this sort of mushy region for that system? Because it's also very similar to, viscous fingering that you see the sort of Saffman-Taylor kind of.
One of the other interests to this is, could you control a material, right, by imposing a flow? Because for a long time, people who grow semiconducting materials would like to control what are the properties, and they're plagued by these instabilities. So one of the ideas is to try to impose a flow and control the properties.
But in this case, you could use it to actually grow structures.
Right.
Yeah.
Because if you want to have a catalytically active surface, let's say you start with an alloy with a very low concentration of the catalytically active component, you can enrich it in the surface by actually removing the rest of the stuff and then just have and maybe refresh it.
File the patent tomorrow, and you fund the next conference. Thank you. Okay, so as I said, if people want to diffuse to lunch, we have to be back here in about an hour or something like that. So there's, where should we go, Axel?
We just go, I thought at least.
Today we can go to the